Hey guys, in this lesson we're going to be getting ready for the Unit 5 exam on waves. Question number 1. Which wave diagram has both wavelength and amplitude labeled correctly? So the best answer for this one is going to be choice 3. And the reason for that is that a wavelength needs to cover a complete cycle of the wave's isolation. So in this case we have both a crest and a trough, so that's a complete cycle and one wavelength. An amplitude, however, is the distance from equilibrium position, which I'm highlighting now, and the area of maximum displacement, or in this case, a crest. It could be a trough as well. But it can't be both a crest and a trough. That would be twice the amplitude. And number 2, it says, as shown in the diagram below, a transverse wave is moving with velocity v along a rope, and velocity v is, in fact, moving to the right. So it is going to be a wave that will pass through x at some point. And the crest and the trough will both travel together along the rope until the crest is the first thing to encounter point x. Now at that moment, point x will rise up on the crest. But once the crest passes through x, the x will be following along the sort of backside of the wave, which I'm sort of highlighting here. So it'll be falling down in that moment until it reaches where the crest used to be, down here, and that will be its lowest point. But after that occurs, after this trough is in x and x is at its lowest point, it then will have to rise up through the sort of upward swing after the trough on its way back to the equilibrium position. Therefore, the best answer for this one is going to be 4, up, then down, then up. Number 3, as a wave travels through a medium, the particles of the medium vibrate in the direction of the wave's travel. So for instance, let's say that the wave is traveling to the right with velocity v, and the particles are vibrating back and forth in that same direction, parallel to the wave's travel. So if that's true, then this kind of wave has to be a longitudinal wave. Number 4, an electromagnetic wave traveling through a vacuum has a length of 1.5 by 10 to the negative 1 meters. What is the period of this wave? So if I use the equation v equals f lambda, I'll be able to isolate for f. And I do that because frequency is the reciprocal of period, as evidenced by this equation. So if I actually want to get the period, I need to get the opposite of frequency. So what I'm going to do is I'm going to say if f is v over lambda, then t is lambda over v. I'm going to use this equation. So it was stated in the question that the wavelength is 1.5 by 10 to the negative 1 meters, and the velocity of an electromagnetic wave in a vacuum is the speed of light. So that's going to be 3 by 10 to the 8th meters per second. So 1.5 divided by 3 is going to be 0.5, and I also need to deal with the exponents as well. So I know that it's going to be 0.5 times 10 to the something, but it's going to be negative 1 minus 8. So what is that? Negative 1 minus 8, I believe that's negative 9, so 10 to the negative 9. And the unit for this is going to be seconds. So let's see if we can find an answer like that. So 0.5 by 10 to the negative 9 is not standard scientific notation. It's actually 5.0 by 10 to the negative 10 seconds, and that is also the reason why I'm choosing choice 1. Number 5, a physics student notices that 4 waves arrive at the beach every 20 seconds, and he wants to know the frequency of these waves. So frequency is defined as the number of cycles of a wave that occur every second, and in the question it was stated that 4 cycles occur every 20 seconds. So that's 1 over 5 as the frequency, or 0.2 hertz. Choice 1. Number 6, what's the wavelength of a light ray with a frequency of 5.09 by 10 to the 14th hertz? as it travels through lucite? So for this question, I recommend the use of two equations, v equals f lambda and n equals c over v. In the first example, I'm going to use the index of refraction to find the velocity of the light in lucite. So after transformation, I get v is c over n. And in the second equation, I will know the v and I will know the f, and I'll be looking for lambda. So to isolate for lambda, I'll get lambda is v over f. All right, so let's plug in variables that I know. So for the first equation, v is c over n, and c is the speed of light in a vacuum, so that's 3 by 10 to the 8th meters per second. And n is the index of refraction for lucite. You can see it right here, it's 1.5. And so, of course, you get as your velocity 2.00 by 10 to the 8th meters per second in lucite. So we'll use that velocity in our second part of this question. So lambda is v over f, and v is 2.00 by 10 to the 8. We just solved for that. And the f is 5.09 by 10 to the 14 hertz. So let's do 2 over 5.09 to begin. And I am getting 0.393 with some other digits, but I'll stop there. And it's going to be times 10 to the something. But in this case, it's going to be an 8 minus a 14, which is negative 6. So 0.393 times 10 to the negative 6 meters. Now, this is not proper scientific notation, so the best answer is going to be 3.93 times 10 to the negative 7 meters, and that also means that your answer is choice 1. Number 7. The diagram below represents a wave. What is the speed of the wave if its frequency is 8 hertz? So v is f lambda, and they are asking for v, and they told me that the frequency is 8 hertz. If I can find out the wavelength from the diagram, then we'll be good to go. So the wavelength is going to be just the distance of one cycle. So I'll mark out the cycles with x's. So that's 1 cycle, 2 cycles, 3 cycles. Now 3 cycles are happening over a distance of 6 meters, which actually means that the wavelength of 1 cycle is only 2 meters. So I'll plug that in here, and the velocity of the wave has to be 16 meters per second. In number 8, we have a Doppler effect question. But basically, what you've got is a police car that's moving at some speed that doesn't matter, and it has a frequency of its siren, which does matter. It's 1,000 hertz. And the police car is approaching the pedestrian. So you need to pay attention to the frequency and the word approach. So since the police car is approaching the pedestrian, then the observed frequency has to be larger than 1,000. Which is why the answer is choice 4. All right, number 9. As a wave travels between 2 points in a medium, the wave transfers energy only. Now, the particles of the medium can vibrate around fixed positions, but they aren't transferred anywhere. Energy, however, will move from place to place through a wave. And in number 10, which diagram below does not represent a periodic wave? A periodic wave is defined as a series of regularly timed pulses. So examples of good periodic waves are choice 1, choice 2, and choice 3. But in choice 4, you have these different pulses. I see 3 different pulses making that wave, and therefore it's the one that does not represent a periodic wave. In number 11, we're asked basically a definition for the spreading of a wave into the region behind an obstruction is called. So that's the definition for something called diffraction. And of course it looks like that. In number 12, we're asked, what is the frequency of a light wave with a wavelength of 6 by 10 to the negative 7 meter traveling through space? Well, if v equals f lambda, then f is v over lambda. And the speed of light in space is 3 by 10 to the 8th meters per second. And the wavelength was stated in the question as 6 by 10 to the negative 7 meters. And if I just do the 3 over the 6 first, I get 0.5. And I still need to deal with the 10 to the 8 over 10 to the negative 7. So in this case, we'll just say times 10 to the, but it's going to be 8 minus negative 7, which of course is 15. We are solving for frequencies, so this is going to have a unit of hertz. And in proper scientific notation, our answer is going to be 5.0 by 10 to the 14 hertz. So answer choice 4. Number 13, compared to the speed of microwaves in a vacuum, the speed of X-rays in a vacuum is the same. Basically, all electromagnetic waves, regardless of type, travel at the same speed in a vacuum. But that's really the only thing that's constant between them. Like for instance, a microwave and an X-ray are traveling in a vacuum. If we compare their wavelengths and periods, we'll notice differences. So the first thing to point out is just to use the electromagnetic spectrum to say that X-rays and their wavelengths will compare to microwaves in that the wavelength, which is up here, of an X-ray is like, let's say 10 to the negative 10. But a microwave, it's like 10 to the negative 2. So X-rays have a much smaller wavelength. That means that the answer cannot be 1 and it cannot be 2. So let's take those out. But for 3 and 4, those are still in the running. And we need to know about their period. I think that it would be helpful to use V equals F lambda to start. Now I know that we are actually being asked about period, but I'm going to do an investigation on frequency. Bear with me. So to solve for frequency, I would say that F is V over lambda. And also on your reference table, you'll find this one, and it says that period is 1 over the frequency. So I'm really asked about period, and period is really the inverse of frequency. So if frequency is V over lambda, then period must be lambda over V. It has to be true. Now, the V is the velocity of the wave, and microwaves and X-rays, as just discussed, will have the same speed in a vacuum, so let's ignore that. And now I am just looking at the direct relationship between period and wavelength. Therefore, an X-ray has a wavelength which is shorter, and therefore it must also have a period which is shorter. So shorter and a period that is shorter. Choice 4 is my answer. So for number 15, we're asked which statement best describes a proton that is being accelerated. And the best answer for this one is that it's going to produce electromagnetic radiation. This is just like a fact that we should remember about electromagnetic radiation, is that it is always a result of a charged particle that's being accelerated. In number 16, it says 2 waves having the same frequency and amplitude are traveling in the same medium. Maximum constructive interference occurs at points where the phase difference between the 2 superposed waves is. So the best answer here is, of course, 0 degrees. 17, 2 waves having the same amplitude and frequency are traveling in the same medium. Maximum destructive interference will occur when the phase difference between the waves is. And that's going to be 180 degrees, meaning that there will be a crest lined up against every trough. In 18, we're asked which 2 labeled points are 180 degrees out of phase. So scanning through the answer choices, I think the best one is D and F, because D is a trough and F is a crest, so these guys are half a wavelength apart. For number 19, we have a wave moving to the right, and they want to know which wave could possibly produce a standing wave with this wave. Now, standing waves need to be 2 waves with the same amplitude and frequency, but they're moving in opposite directions, which of course is going to make my answer 3. 20. The diagram below represents a light ray being reflected from a plane mirror. From the data given in the diagram, what's the angle of reflection? So it seems like it's going to be listed here because the angle of reflection or the angle of incidence, in both cases, they are measured between the ray itself and the normal. So yeah, I'm going to go with 50 degrees as my answer. In 21, we want to know which diagram best represents the path taken by a ray of monochromatic light as it passes from air through the materials shown. So I have a couple of things to discuss about this question. The first one is just right away, I know that the answer has to be 2. But there's so much I want to say about this question, so don't tune out yet. But the first reason why it has to be 2 is that I noticed that the ray entered from the medium air and it exited into the medium air. So if that's the case, if you both exit and enter from the same medium, then that means that you have to enter and exit from the same angle as well. So the fact that this angle is the same as this angle is already proving to me that the answer is choice 2. But wait, there's more. We also need to consider at every boundary, is the ray bending towards the normal or away from the normal? And you guys need to know that if you move to a medium with a higher index of refraction, then that means you'll bend towards the normal. And of course, if the second medium has a lower index of refraction than the first, the ray would bend away from the normal. So I will use the index of refraction to apply those indices. So I put them into the diagram here, and I would just point out that as you go from this medium to this medium, the index is increasing. So that means that we need to be bending towards the normal. And you can see that that's true. This represents the angle between the normal and the incident ray, but right here you can see that the angle is in fact smaller than that. So we bend towards the normal. But when you go from flint glass to water, you should actually bend away from the normal because the index of refraction is decreasing. So here's the index right here, this is the angle, and then you can see that the angle is larger on the other side. And then on the other hand, when we go from water to air, we're going to be decreasing that index again, so we will need to bend away from the normal again. So here's the angle on the way into the boundary, and here's the angle on the way out, so we bent away again. So I can still confirm that choice 2 is the right answer. All right, so in 22, we have a straight glass rod, and it's being placed in a beaker of water, and what's the best explanation for the phenomenon pictured, which is that the straw has been bent? And we would just say that light is refracted as it crosses the air-water interface. So in 23, they ask what occurs when light passes from water into flint glass. So water's index of refraction is 1.33 and flint glass is 1.66. So I know that it will have to slow down as it increases its optical density. So yeah, the light will travel slower in flint glass. So it can't be 3 or 4, it has to be either 1 or 2. But check out the equation V equals F lambda for the rest. Because the frequency can't change during this process, we're really just observing the direct relationship between velocity and wavelength. And we just said that the velocity will decrease, and that means that the wavelength will also decrease, and therefore choice 1 is the best answer. All right, 24, we're going to base our answer on this diagram. We have this ray of light at 5.09 by 10 to the 14th hertz. It's moving from water into medium X. The angle of incidence is 45 degrees, and the angle of refraction is 29. So everything they said there is in the diagram. But let's calculate the absolute index of refraction of medium X. I suggest thinking about this one in terms of Snell's law. And I'm going to think of N2 as being the absolute index of refraction for medium X. So algebraically, N2 is equal to N1 sine theta 1 over sine theta 2. Let me plug in the variables that I know. If N2 belongs to medium X, then N1 belongs to water, and water's index of refraction is 1.33. And the theta in water is 45. The angle in medium X is 29 degrees, so for sine theta 2, I'm going to write sine 29. And from here, I need to solve. And I got 1.94 as my absolute index of refraction. And I can see in number 25 that we'll also get to use Snell's law. We're asked for the sine of angle theta x, so I'll just treat that as sine of theta 2, which is going to be equal to n1 sine theta 1 over n2. I'll plug in variables that I know. So I chose 1 as n1 because it was for air and then sine of 30, but I need the index of refraction for medium 2, which is lucite, so I found it here, it's 1.5. And I got 0.333, so my answer is choice 1. All right, number 26. The speed of light in a material is 2.5 by 10 to the 8th meters per second. What is the absolute index of refraction of the material? So we can use the equation n equals c over v to discover this. The absolute index of refraction is n, so we don't need to rearrange. C is the speed of light in a vacuum, which is 3 by 10 to the 8th meters per second, and v is the speed of light in that medium, which in this case is 2.50 by 10 to the 8th. The 10 to the 8 part cancels, and this ends up being 3 over 2.5, which is 1.2. So my answer, again, is 1. All right, number 27. A ringing bell is located in a chamber, so this is sound waves, and those are mechanical and longitudinal, as a side note. But if you put that bell in a chamber and then remove the air, you can see the bell vibrating, but you can't hear it. The reason for that is that light waves, since they're electromagnetic, can travel from the bell through the vacuum of the chamber and to your eye. However, sound waves are mechanical and require a medium. So my answer is 1. In 28, we have a 512 hertz sound wave traveling 100 meters to an observer through air at STP. So I know the velocity of sound at STP, by the way. And we want to know the wavelength of this sound wave. So let's use the equation v equals f lambda. Since they want to know the wavelength, let's rearrange for that. The wavelength is going to be v over f. And the velocity of sound in air at STP is 331 meters per second. It's on your reference table, by the way, on the front page. And we have to divide that by the frequency of the wave, which in this case was 512 hertz. And after that calculation, I'm getting 0.646 meters as the wavelength of this wave, or choice 2. In 29, which wave phenomenon occurs when vibrations in one object cause vibrations in a second object? This is just a description of resonance, something that affected the Tacoma Narrows Bridge and also is responsible for the ability to break a crystal glass using only sound. In 30, we actually are charged with using a protractor and a straight edge to construct the refracted ray representing the light emerging at point P into air. So I don't have a protractor that I can use digitally, but I can tell you the way you need to draw these diagrams, and I'll have to trust in your protractor skills. But basically, the ray is coming in at an angle of 35 against the normal. It makes some changes and some non-changes, and then it reflects, comes back at the same angle against the normal. But we want to know the ray as it exits. Now remember, if it enters from air and exits into air, it has to adopt the same angle on the way out. So you're going to need to draw a line that's basically identical to, but a reflection of, the incident ray. So I have no clue how close I really am to being accurate there, but just make sure it needs to be 35 degrees against the normal on the other side of the normal. So let's say I've done number 30, and we'll take a look at 31. Calculate the angle of refraction of the light ray as it enters the corn oil from the air. So this is going to be a Snell's law question. N1 sine theta 1 is N2 sine theta 2, and we are looking for the sine of theta 2, and then we'll need to do an inverse sine to isolate theta. So I've gone ahead and done that, and now I can plug in the data that I know. N1 is for air, and its index of refraction is 1. And the first angle, the angle of incidence, is 35 degrees, so sine of 35. And N2 is for corn oil. Corn oil's index of refraction is, let's see, here, 1.47. So let me get rid of that, and then I'll apply 1.47, and then solve. So without doing an inverse sine, I'm getting 0.390 for the sine of theta 2. But you can do an inverse sine on that. And when you do, you will get the answer 22.966, or let's say 23 degrees. So theta 2 is around 23 degrees. All right, let's do 32 and 33. So 32, explain why the ray does not bend at the corn oil glycerol interface. So the reason for that was because the corn oil and the glycerol had the same index of refraction. For 33, they want us to mark an X on the wave at a place that is 180 degrees out of phase with point A. I find that a little bit challenging. What I find less challenging is to just find a point that's in phase with point A, or 360 degrees away. So I can see that that point would be here. So this would be, I'll call it A prime, and I'll say it's 360 degrees away from A. So I'll go ahead and mark that. And now I can see that half of that is going to be the answer. So it's going to be like right around here. And I will just mark it, I'll mark it in red. And we will have to label it point X. And that's going to be 180 degrees out of phase with point A. And we went ahead and finished just now. So here is a scan of the answer choice, or the answers, in case you just want to be sure of anything and catch any mistakes I may have made. But thanks for watching, and don't rely just on this video as you prepare for the test. Also, be smart about this. Think about anything that is a problem area for you and work on that especially hard. I believe in you. I can't wait for you to show mastery on this exam, and thank you for watching.